Okay, so in this video, we'll take a look at example 411, just talking through the method of analysis. And so thinking about this wire loaded at B, so B is going to move about C, C is going to move with respect to D, and D is going to move with respect to G. And so our goal here is to quantify how much B moves, how much B moves due to the fact that D and C are also moving with respect to the fixed point in space. And so what we talked about in class was how link CB is going to have bending moment, and we are told to neglect shear, so we're not going to worry about that. We're only tracking it so that we can show that it acts through the members. So for CB, we're going to look at bending. For CD, we have both torsion and bending. And then at D, we have two bending directions as well as compression due to that shear force I was talking about. So then as we're analyzing these sections of the wire, on link section BC, we know that the moment is going to change starting from B going to C by Fx, where x is going from 0 to A. And then as we look at CD here, we see the torque is going to be constant. The torque about CD is going to be constant and equal to F times the length A. The moment of C about D, the one that's causing C to move out around D, that's F times X, where X goes from 0 to B. And then as we continue on for link DG, we have an axial force that I just want to say out loud there, and this is compression. And we have moments, both due to F out a distance B and F up a distance A. And so both of those, let's see, up a distance A is going to be pushing D down, and out a distance B is going to be pushing D over. And so all of that is contributing to the motion of point B. And so we're going to use these pieces to generate our deflection statements, and we're going to generate 1, 2, 3, 4, and then 5 deflection statements to ultimately sum up to the deflection of point B. So as we think about length BC, I know that my bending moment is Fx. The derivative of the bending moment then just goes to x. And so I set up my deflection. It's the integral from 0 to A. And we have our bending moment deflection equation here evaluated with respect to x. Oops. So that all evaluates to f a cubed over 3ei. So for CD, we're going to have a similar expression for bending, and then we also have to account for the torsion. And here we said that the torsion is F times A, and we'll go ahead and take the derivative of the torsion with respect to its force. And so that will be the first component here will have the integral of my torque, F times A, my derivative, A, all over my Gj for torsion, and we'll evaluate this with x from 0 to b. And so this piece is my first part of the integral. We'll also have that second part of the integral from 0 to b of f times x. That's my moment. We have EI because this is my bending, and we'll evaluate with x. And so those are the two terms for my deflection CD. So ultimately that evaluates FA squared B over JG due to torsion, and this is my bending. Looks the same as my first bending, except that my length is B here now instead. So on we go to DG. So we're going to account for both axial and bending here, and in the axial direction we'll have the integral from 0 to C of F over A, So F over AE with along the X direction, everything being constant. And then we'll also have our bending. Here, our moment is constant. So our moment is FB in the one sense, and then FA, so FB here and FA here, and those are both constants. So you can see FB, and then the derivative of that is just the length B over EI. So this is my bending due to the force out at an arm B. And then we have the same here, FA, the derivative there is A. And so we evaluate all three of these integrals from 0 to C. Nothing changes with respect to X. And so all of these are essentially summed up and multiplied by C. And so we might represent that here as FC over AE plus FC over EI times the quantity A squared plus B squared. That's my delta of DG. Keep in mind, what we were really looking for was the deflection of point B. So now we're going to take the deflection of BC plus the deflection of CD plus the deflection of DG and add them all together, and that's how much the point B is actually moving due to these different types of motion. And so that's the goal of this problem, example 411.